discussing a presentation by Jimmy Ma. He's talking about sort of the question whether large language models can be scaled and how this time might be different than maybe just before when we had the ImageNet moment. He's comparing ImageNet with ChatGPT. So we had ImageNet moment and now we have ChatGPT moment. How it's different, if at all, if it's different, how we should position ourselves, what the opportunities are, scalability, impact. He's a pretty thoughtful person. I like him a lot. He has this relatively soft and unassuming attitude that still can generate a lot of depth. He is an assistant professor at Toronto. He's also at X.ai. He comes from the Jeff Hinton stable, so he's, I would say, in that school of fundamental neural nets, thinking fundamentally, really, what is chain of thought? Why does it even work? What is the fundamental reason why we have large language models the way they are? Like things along those lines. So the main takeaway of the talk is that in a nutshell, compute matters, scale matters to some extent, but compute is a lot more important. So you can have a smaller model, but you can apply a lot more compute to it. What does that mean? That means you can have a more complex transformer architecture, with more relationships. It also means that, sort of paraphrasing Richard Sutton, that we really can solve intelligence with compute and search. I think he goes in that same direction. So this is related to Richard Sutton. And I want to draw that line, even though Richard Sutton came up in the Sergey Levin talk, which, by the way, was at the same event. It's interesting to see the parallels here. So Jimmy talks about the sort of fundamental differences of LLMs versus the previous generation of classification models that came out of ImageNet. He also talks about some very specific ideas of how to improve them. The fundamental difference is that in a large language model, you can improve the model, you can align the model to be better at delivering a task without changing the weights. That was not possible before, and this offers huge scaling opportunities. This is an Not Even Wrong podcast. It's January 29, 2024. This is Krim Delko. This is the second installment of today. For the year, down 16.7%. The market's up 10.1%. We're underperforming by 27.7%. So Jimmy Ma is at the same event like Sergey Levin, the previous episode of today. He gave a talk, and I thought it's useful to also discuss this talk. Jimmy is a assistant professor at Toronto, so he's really in the sort of footsteps of Jeff Hinton, Ilya Sutskever, Alex, whatever his name was. So those people who, AlexNet. I mean that's as clean of a lineage as it gets. This is AI high society, if you will, and he has this unassuming, calm, deep voice, explaining things relatively slow, but still with a lot of depth. So his main question is, what's the difference between the age of ImageNet versus the age of LLMs after ChatGPT? And the fundamental difference is that with LLMs, we have massive scaling opportunities because we can improve them with compute. This is the first takeaway. The bitter lesson, which says that, or Sutton in his essay talks about the ability to get closer, to converge towards intelligence through compute and search, and not explicit knowledge. I think this is related because what Jimmy is talking about here is very similar. He is talking about some research that he has done or that he's aware of that shows that if you increase a model size, you actually see sometimes divergence. You see a reduction in performance, but in increase of compute always increases the performance. Now, this is interesting. Why does model size potentially decrease performance? Jimmy talks about the potential interpretation, which is that with size, you actually get better at imitating humans. And humans make mistakes, particularly in logical type questions, and or transitivity type stuff. So if I like B better than A and C better than A, then I should like B better than A. Like things like that. Humans are not very good at that. There's lots of heuristics. Kahneman, Tversky talked about this. So a lot of these shortcuts that humans do that defy logic, they could become a problem in large language models, because what they're doing is really drawing from a data set that has been created by humans. Let's not forget what large language models are. Large language models are a compressed representation of reality that is present in the internet. And the internet is a data set which was created by humans primarily. And particularly the words in the data set are created by humans. So if you increase the model size, you will see sometimes a decrease in performance. Now, I didn't want to go too deep into that. I find that just interesting, and really the conclusion is that an increased amount of compute, so it's really compute per flop, compute per token, energy unit per token, dollar per token. Those are the kinds of things that we care about, because tokens are directly related to the amount of compute. I think two interesting takeaways from the talk, though, in particular, I want to talk about APE, which is an automatic prompt engineering framework. So the other big thing, let me get back to the fundamental question. Okay, what is different between the age of ImageNet and the age of large language models? And the difference is that with ImageNet, you have a fixed model that is getting better with better data and more data. With an LLM, you have a generalizable model that can be improved without changing the weights through prompt engineering. And that is driven by the chain of thought concept. The chain of thought concept is the fact that you have a massive amount of, a massive dimensionality of data distributions. In other words, you have a lot of text and a lot of words, and they all fit into all kinds of different patterns. And when certain data is localized within a region of those patterns, then you can infer a lot of stuff there. But what you can do is also you can chain those regions together, and that's what prompts do. So you can actually connect a dolphin with a bicycle and have a dolphin ride a bicycle. At least potentially, you could do that by chaining those two data distributions that have been trained separately. You've been trained on, the model's been trained on dolphins, and the model's been trained on bicycles, but it has never seen a dolphin riding a bicycle. With chain of thought, you can link those two concepts. In that context, you can also align a large language model better with the task at hand by chaining it with prompts. And the prompts are human engineered. Prompt engineering is a profession, but what APE is intending to do is actually automate that, have a hermetically sealed self-referential self-improvement through automatic prompt engineering and scoring. So what you need, of course, if you do something like that, this is akin to reinforcement learning. What you're going to need is some sort of reward function, something which decides whether you're on the right path or not. And if and that reward function is in the case of APE, the paper, it's some sort of benchmark that tests. So you prompt X, you see what the model produces, and the better you get, the closer you get to a good score in the benchmark, the better the prompt. And you're going to do this in a sort of almost multi-layer way, where you're going to start with random prompts and do a lot of prompting, and then you pick some of the best prompts and then fine-tune them, so you kind of produce a pyramid. Now, there's some technical issues, some engineering solutions to problems such as compute, memory, in I/O stuff. There's a lot of engineering solutions that can be that can be applied to this problem. But just generally, what I wanted to discuss here is go back to the chain of thought paper that was presented in NeurIPS. Why do we think step by step? Why is chain of thought a useful thing? Well, it comes from psychology, and the results show that that direct prediction is often inaccurate for some inferences because the relevant variables are rarely seen together, right? So predicting a dolphin riding a bicycle, let's say in a surrealist painting, Dali painted a dolphin riding a bicycle. That's something that the model has never seen. So it's relatively difficult to predict that type of word from the data distribution that an LLM has been trained. However, if you chain it, if you say, well, sometimes in surrealist paintings, things can be shown that are unusual. For example, something that's unusual would be a monkey riding a motorcycle. And then you could go, now please finish the following sentence. I saw a dolphin riding a, and then it could fill it up with motorcycle or bicycle. So you kind of chain those things together. So that's one reason why chain of thought works, is because you have data which is localized because it's been trained together, it's seen together lots in training, but never, and therefore it's localized. Yes. Second, chain of thought reasoning improves estimation by incrementally chaining local statistical dependencies that are observed frequently in training. So this is kind of the same, I think, like the first, I mean, very similar. They keep going. They say we also find that the combination of locally structured training data and reasoning with self-generated intermediate variables yields much greater data efficiency than training on data containing all variables. So what that means is that you have the chain of thought works really well when you isolate the data set and really only work with the local regions that that the data is. What this means in practice is, if you want to write a poem about a dolphin riding a bicycle, you're much better off chaining the model towards the regions of dolphins and bicycles and then stay in that realm than having all the data during inference time. Fundamentally, let's get back to Jimmy Ma's presentation. What he's saying here is, again, you can change the way, without changing the weights, you can align the model better with tasks, which is important. And it also yields to the question, okay, can we scale these things? Yes, we can scale them, because it's about compute, and we know that from GTC that is a big deal, and that's beautiful. I think that's why the AI complex with NVIDIA and Broadcom and all the other companies are going to do extremely well. The other big takeaway from this talk is explainability, which is related to chain of thought, because you have this concept of chain of thought, which is really, let's say, if we had a which is an automatic prompt engineering technology which generates, think of it like more like this is like a program. Okay, this is literally programming the LLM. And if we have a chain of prompts that is designed to deliver a certain task, well, then we also have explainability. So explainability and chain of thought are very closely related. And to me, that's a little bit more, so there's a bit more depth here than it might seem in the beginning, because this could be the path towards explainability. These are not black box models. Maybe the model itself, the LLM, might be a black box thing where there's all these dependencies and patterns that we found in the data. But when it comes to task execution through chain of thought, we actually have the chain of thought, which is the explainability. So in my opinion, that's a pretty strong argument for these types of approaches. So to summarize, I think Jimmy Ma's talk was interesting for a couple of reasons. One is he asks a very simple question: what is different today than, let's say, during the ImageNet times? And the answer is we can tweak models, fine-tune them, we can adapt them to tasks without changing the weights, which has huge scalability implications. Second, he's also offering an automated way to prompt engineer models, in other words, to align them, to program them. So we could use large language models actually as programmers, and the programmer is the prompter, and the prompts can be generated automatically and then scored against scoring functions. And finally, what he says is that chain of thought is also the explainability. So the path towards chain of thought and better execution of the models, or better alignment of the models, is also the path towards explainability. Thank you.